Today we'll discuss ISI's 2021 BStat BMath UGB paper, and the first question is, there are 3 cities, each of which has exactly the same number of citizens, say n. So suppose we have 3 cities, say C1, C2 and C3, and each of the city has n citizens. Now let n citizens in C1 be A1, A2, AN. For C2, let them be B1, B2 and BN, and for city 3, let them be D1, D2 and DN. That says each citizen in each city has exactly a total of n plus 1 friends in the other 2 cities. Now show that there exist 3 people, one from each city, such that they are friends. Now we'll solve this question using contradiction. So what we'll do is we'll say that let there be no 3 people which are friends. Now in order to prove this question, what we'll do is we'll say that out of these 3n people, let there be a person with minimum number of friends in any one city. So out of all these 3n people, without loss of generality, let us say that this A1 has least number of friends in city 2. And let that number be K. So A has K friends in city 2. That means for any other person, number of friends in any one city, it will be K or greater than K. So if A has K friends here, A will have n plus 1 minus K friends in C3. Now, are these K friends of A1 in the city 2, let us choose any one friend, say B1. And since K is the smallest number, B1 will also have at least K friends in city 3. Now our assumption says there are no 3 people which are friends. So that means if B1 is a friend of A1, then in city 3, no friend of A1 can be a friend of B1. So this B1 will have K or more friends in city 3 which are other than this n plus 1 minus K friends of A1. So if we count number of citizens in city 3, it will be greater than or equal to this number n plus 1 minus K and then plus K. That means number of citizens in city 3, it should be greater than or equal to n plus 1. But we are given that this number is equal to n. That means there is a contradiction. So from contradiction, we can say that there exist 3 people, one from each city, such that they are friends. Now question number 2 is, we are given a function f which is defined on integers such that f0 is unequal to 0 and f1 is equal to 0. Assume that f satisfies the following 2 equations. We need to find set of values of this function f. That is, we need to find a range of this function. Now from this first equation, if we put x as 0 and y equals 0, we'll get f0 equals f0 plus f0 minus f0 square. I'll cancel. So from here we can say either f0 is 0 or value of f0 is 1. Now we are given that f0 is unequal to 0. That means it is not possible. So the value of f0 will be simply 1. Now what we'll do is, in this second equation, we'll put y as 0. Now if we put y as 0, we'll get this as fx into f0 will be f0 into fx into f0. Now f0 is 1. So from here we can write fx square minus fx equals 0. That means value of fx is either 0 or value of fx is 1. So this function fx can take only 2 values, 0 and 1. That means range of this function is simply 0 and 1. And that's your part A. Now in part B it says that assuming that there is a non-zero integer a such that f is unequal to 0, then prove that the set B fb unequal to 0 is infinite. So now we have any non-zero integer a such that f is unequal to 0, and since range of this function is 0 and 1, it means fa it is equal to 1. Now we need to prove that if f is equal to 1, then there exist infinite points b such that fb is unequal to 0, that is fb is equal to 1. We'll prove that f minus na will be 1 for all n belongs to natural numbers, and we'll prove this result using induction. So let the statement be Pn. Now first we'll prove P1 is true. Now if we put n as 1, we'll get f minus a equals 1. Now in this equation, if we put x as 0 and y as a, we'll write this as f minus a into f0 into fa will be equal to f0 into f0 into fa. Now f0 is 1 and fa is also 1. So from here we can say f minus a equals 1, that is P1 is true. Now the second step is we let Pk be true. So if Pk is true, that means f minus k is equal to 1. From here we have to prove that Pk plus 1 is true. Now Pk plus 1 is f minus k plus 1a. For that what we'll do is, in this second equation, we'll put x as minus ka and we'll put y as a. We can write f minus k plus 1a into f minus ka into fa will be equal to f0 into f minus ka into fa. Now f minus k is 1, fa is 1. So from here we can say f minus k plus 1a is also 1. So P1 is true, and assuming Pk to be true, Pk plus 1 is true. That means from induction we can say that the statement Pn is true. So if we have any non-zero a, then we'll have infinitely many points where this function is non-zero. Now the next question is, prove that every positive rational number can be expressed uniquely as a finite sum of the form a1 plus a2 upon factorial 2 plus a3 upon factorial 3 up to an upon factorial n, where an it lies between 0 and n minus 1, both inclusive, for all n greater than 1. Now what we'll do is, we'll say let that rational number be x, and we have to prove that we can write this x as a1 plus a2 upon factorial 2 plus a3 upon factorial 3 up to an upon factorial n. Now what we'll do is, for any real number x, we'll define a sequence, and we'll define the sequence as this x1 equals x, and we'll write any ai, it is greatest integer function of xi. So in this case, a1 is greatest integer function of x1, and we'll define xi plus 1 as I plus 1 into xi minus ai. That means x2 will be 2 into x1 minus a1. Now what is x1 minus a1 into 2? x1 minus a1 into 2 will be a2 plus 2 into a3 upon factorial 3. And the same way, if we consider x3, it will be 3 into x2 minus a2. So here factorial 3 will cancel. So again, greatest integer function of x3 will be a3. Here get a function of x2, it'll be a2. So now we can define this number x as this summation I varies from 1 to infinite ai upon factorial I. And if x is any rational number, then this sum will terminate at some n where xn will be 0. Now since ai is greatest linear function of xi, then we can write xi minus ai, it will be greater than 0 but less than 1. Now if we multiply it with I plus 1, we can write I plus 1 xi minus ai will be less than I plus 1, and this is nothing but this is xi plus 1. So from here we can write xi plus 1, it will lie between 0 and I plus 1. Now ai plus 1 is nothing but it is integral part of xi plus 1, and integral part of x is always less than or equal to x. So from here we can say ai plus 1 will always lie between 0 and I. Now we take I plus 1 as n, we can write any an, it will lie between 0 and n minus 1. So this is true for any real number, and if it is a rational number, then it will terminate at some number n. Now question number 4 is, let g be a differentiable function whose derivative is continuous and such that g of gx equals x for all x greater than 0. And if g is not an identity function, then prove that g must be strictly decreasing. Now again we'll solve this question using contradiction. So what we'll do is we'll say let g be not strictly decreasing function. So if it is not strictly decreasing and if it is not an identity function, that means for some x, g must be strictly increasing. Now for such points, if g is increasing, gx is unequal to x, then either gx is greater than x or gx is less than x. Now if we take composition of g, we can write g of gx will be greater than gx. Now since g is an increasing function, sign of inequality, it won't change, and gx is greater than x. Now it is given that g of gx, it is equal to x. So from here we'll get this condition that x is greater than x, which is not possible. So this gx, it cannot be greater than x. Now if we consider the second case where gx is less than x. Now again if we take this composition of g, then we can write g of gx will be less than gx. Now gx is less than x. Now g of gx again is x. So from here we can write x is less than x, which again is not possible. So for both the cases, we are getting conditions which are impossible. So from contradiction, we can say that this g, it must be strictly decreasing for all the values of x. Now question number 5 is, we are given this polynomial px, which is x to the power 20 plus ai x to the power I for all i's from 0 to 19. So we can write this polynomial px as x to the power 20 plus a19 x to the power 19, a18 x to the power 18 plus a1x plus a0. Now it says if p of x equals p of minus x for all x belongs to R, that means its odd coefficients, they must be 0. So a2n plus 1, they'll be 0. Then in that case, we can write this polynomial px as x to the power 20 plus a18 x to the power 18, a16 x to the power 16 up to a2 x square plus a0. Now we are given that pk equals k square for k equals 0, 1, 2 up to 9. Now what we will do is we'll consider this equation, which is px minus x square equals 0. Now this equation has 10 real roots, namely 0, 1, 2 up to 9. Now since px is a polynomial with even powers and power of x square is also even, that means if alpha is the root of this equation, then minus alpha will also be the root of this equation. So the roots of this equation must be plus minus 0, plus minus 1, plus minus 2 and plus minus 9. Now degree of this equation is 20 and now we have 20 roots of this equation. So we can write px minus x square as x square into x square minus 1 square, x square minus 2 square up to x square minus 9 square. Now we need to find this limit x tends to 0, px upon sine square x. Now if we divide everything with sine square x, we can write px upon sine square x minus x square upon sine square x LB x square upon sine square x square minus 1 square into x square minus 2 square up to x square minus 9 square. Now we take this limit x tends to 0, then we can write this as limit x tends to 0 px upon sine square x minus this limit is 1. Now this limit is also 1, and if we put x as 0, we'll get this as minus 1 square into minus 2 square up to minus 9 square. So minus 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 9 times will be minus, and then 1 square into 2 square into 9 square. So it will be 1 into 2 into 3 up to 9 whole square, which is factorial 9 square. So value of this limit x tends to 0 px upon sine square x will be 1 minus factorial 9 whole square, and that is the answer to this question. Now question number 6 is, if a given equilateral triangle of side length A lies in the union of 5 equilateral triangles of side length B, then show that there exist 4 equilateral triangles of side length B whose union contains A. Now we consider a trivial case where this A is equal to B by 2, then for this equilateral triangle with side length A, we'll have four triangles whose union is going to give us this equilateral triangle with side length A. Now for the second case, if A is greater than B by 2, so if we draw these triangles a little bigger, then also union of these four triangles will also contain this equilateral triangle delta. Now we consider this third case when A is less than B by 2, then suppose we have 4 equilateral triangles formed from B, and then if we consider this A, then in order to cover this remaining part of A, we need more than 5 triangles. So in this case, union of 5 equilateral triangles, they cannot contain this triangle delta. So this case is not possible with 5 triangles. So if 5 equilateral triangles, their union gives us this triangle delta, then either the value of A must be B by 2 or it must be greater than B by 2. For A less than B by 2, no such case is possible. So in all the possible cases with 5 triangles, this case when union of 4 triangles will contain delta. Now question number 7 is, let A, B, C be 3 real numbers which are roots of a cubic polynomial and which satisfy A plus B plus C equals 6, AB plus BC plus AC equals 9, and suppose A is less than B, it is less than C, then we need to show that A lies between 0 and 1, B lies between 1 and 3, and C lies between 3 and 4. Now we have a cubic polynomial whose roots are A, B, C. We can write x minus A into x minus B into x minus C. It must be equal to x cube minus S1, which is A plus B plus C. So it will be minus 6x square plus 9x and then plus some constant, say lambda, and let this be this polynomial fx. Now if we find f dash x will be 3x square minus 12x plus 9, so it will be 3 and then x square minus 4x plus 3. Critical points are x minus 1, x minus 3, that is x is 1 or x is 3. Now this is 1 and this is 3, so plus, minus and plus. So it will have a local maxima at 1 and it will have a local minima at 3. Now since this function, it has 3 real roots, the graph should be drawn like this. Now at 1 we have a maxima and at 3 we have a minima. That means value of f1 it should be greater than 0 and value at 3 it should be less than 0. Now we find f1 will be 1 minus 6 plus 9 plus lambda, which is lambda plus 4, and it will be greater than 0, and f3 will be 27 plus 27 minus 54, that is lambda, and it should be less than 0. So this cubic equation can have 3 real roots only if f1 is positive and f3 is negative. That is, the value of lambda, it should lie between minus 4 and 0. Now if we find f0 is lambda, and f1 will be lambda plus 4, then f0 into f1 will be lambda into lambda plus 4. Now lambda is negative and lambda plus 4 is positive, so plus into minus is minus. Now f0 into f1 is less than 0. Now since f it is a continuous function and f into fb it is less than 0, that means at least one root of this equation will lie between 0 and 1. So from here we can say at least one root will lie in the interval 0 to 1. Now if we find f3 is lambda, then f1 into f3 it will be again lambda plus 4 into lambda, which again is less than 0. So from here also we can say at least one root will lie in the interval 1, 3. And now if we find f4 will be 64 minus 16 into 6, 96 plus 36 plus lambda. Now this is 100 minus 96, so this again is lambda plus 4. So we can write f4 is lambda plus 4, and then f3 into f4 is lambda into lambda plus 4, which again is less than 0, which means at least one root will lie in the interval 3 to 4. Now since it is a cubic equation, it cannot have more than 3 real roots. So that means exactly one root will lie in 0, 1, exactly one root will lie in 1, 3, and exactly one root will lie in 3, 4. Now since a is less than b is less than c, so a will lie between 0, 1, b will lie between 1, 3, and c will lie between 3, 4. And that is the answer to this question. Now question number 8 is, a pond has been dug at the Indian Statistical Institute as an inverted truncated pyramid with a square base. The depth of the pond is 6 meter. The square at the bottom has the side length 2 meter and top square has side length 8 meter. Water is filled at a rate of 19/3 cubic meters per hour. At what rate is the water level rising exactly 1 hour after the water started to fill the pond? If we look at its lateral projection, we can draw this pond like this. Now this is truncated portion. And suppose at any point water level is here. Now we join this. Now this length is 2. So here LB1. This is 8. So here LB4. The height of this tank is 6. And let this be some y. Now we write tan theta for this small triangle LB 1 upon y, and LB equal to tan theta of this larger triangle, which is 4 upon 6 plus y. So from here we can write 6 plus y equals 4y, that is value of y is 2. So in this case this length is 2. Now suppose this height is h and this length is x. So here will be x by 2. So again, if we write tan theta, we can write x by 2 upon h plus 2. It will be equal to 1 by 2, or the value of x is h plus 2. Now we can write equation for volume of water in the pond. Now volume water in this pond will be 1 by 3 into area of the base x square into its height, which is h plus 2, minus volume of this truncated pyramid, which is 1 by 3 and then 2 square into 2. So we can write this as 1 by 3. Now x is h plus 2. So we can write this as h plus 2 whole cube minus 8. Now first we'll find the value of h after 1 hour. Now if water is filling at a rate of 19 by 3 cubic meter per hour, then after 1 hour, value of V is 19 by 3. So it is 19 by 3 and L be equal to 1 by 3 into h plus 2 whole cube minus 8. Now 3 and 3 will cancel. So from here we can write h plus 2 cube will be 19 plus 8, which is 27. So we can write h plus 2 as 3, that is value of h is 1. So we need to find rate of change of height when the value of h is 1 and when the value of v is 19 by 3. And in order to find dh by dt, we differentiate this function. We can write dv upon dt will be equal to 1 by 3 into 3 into h plus 2 square into dh by dt. Now 3 and 3 will cancel. Now dv by dt is 19 by 3. H is 1, so it will be simply 3 square into dh by dt. So from here we can say the value of dh by dt will be 19 by 27 meter per hour. So after 1 hour, this is the rate at which height of water column is increasing in the tank.